In this video, we'll talk about hypothesis testing and p-values. The aim is to understand the structure, philosophy, and interpretation of hypothesis tests. So we've discussed confidence intervals, where we estimated a parameter, for example an effect of treatment, and then we estimated a range of plausible values for the parameter. We'll now discuss a different tool of statistical inference called hypothesis testing. A statistical hypothesis test allows us to assess whether the observed difference we find in a study could be due to chance as opposed to a true difference. Chance is estimated using a p-value. P stands for probability. A p-value is the probability of observing such extreme data given the null hypothesis is true. So the null hypothesis is typically stated as no difference, no effect, etc. So say for example we were interested in the difference in 5-year survival between two treatments for a disease. The confidence interval would provide plausible values for the population parameter of interest, i.e. the difference in survival, whereas the p-value estimates how likely it is to observe such a big difference if the true value for the parameter is 0. So the p-value estimates the strength of evidence against the null hypothesis. So p-values and confidence intervals are two different things. Hypothesis testing can be broken into 3 steps. First of all, turn a research question of interest into a statistical hypothesis, that's a null hypothesis. Secondly, calculate a test statistic based on the observed sample data. And lastly, calculate a p-value and interpret and evaluate the hypothesis in light of that p-value. So we'll talk a little bit more about each of these steps. So in statistics, the focus is on the null hypothesis. This tends to be framed in the opposite direction to the scientific hypothesis that typically motivated the study in the first place. So a typical null hypothesis states there's no difference or no association or nothing going on in the population. It has to be unambiguous and testable. We then have an alternative hypothesis that picks up all the alternatives to the null. Now the alternative hypothesis is often the research hypothesis. So it's important that we understand what the null hypothesis is because the p-value is attached to the null being true. So the probability of observing our data if the null hypothesis is true. We would not be able to calculate the probability of observing our data under the alternative hypothesis because that one is ambiguous. It just states not equal to or there is an association, etc. So we would need to specify how unequal, which would be tricky and subjective in many cases. Hence the focus on the null hypothesis. Now let's look at an example, and we use this example as we go through the 3 steps. So our research question is, do babies born in a deprived area of Bristol have different birth weight compared to the national average of 3.4 kilograms? So our null hypothesis, abbreviated H0 here, is that there's no difference in mean birth weight between babies from the deprived areas and the national average. So the population mean in the deprived is equal to 3.4 kilograms. Now the motivation that led to this study being done, on the other hand, was probably that there is a suspected difference. But this is written as the alternative hypothesis, abbreviated HA. And here we say that the population mean does not equal 3.4 kilograms. So we can actually write that another way and it means the same thing. So this mu stands for the population parameter that we're interested in. So the population mean of birth weight in the deprived area is equal to the population mean in the rest of the UK. And likewise for the alternative hypothesis, the population mean in the deprived area does not equal the population mean in the rest of the UK. Now, in order to calculate the probability of observing our data if the null hypothesis is true, i.e. the p-value, we calculate something called a test statistic. This test statistic follows a known sampling distribution. And a sampling distribution is actually a probability distribution. All sampling distributions are probability distributions. And this particular one explains the behaviour of the test statistic over infinite random samples under the null hypothesis, so we can work out the probability of observing that test statistic under the null hypothesis. So it's just exactly like a sampling distribution for a point estimate that we've already talked about in confidence intervals. Now this is a general form for a test statistic. It is the point estimate divided by the standard error of the point estimate. So let's go back to the example. So our research question was, do babies born in the deprived area of Bristol have a different birth weight compared to the national average of 3.4 kilograms? So we collect some data from a random sample of 50 babies born in deprived areas, and we work out the sample mean, that's 3.22 kilograms. So our point estimate, or the difference that we're interested in estimating in the population, is 3.4 take away 3.22 kilograms. We also estimate the standard deviation in our sample, that's 0.6 kilograms, and from that we can work out the standard error, which comes to 0.085. So if we plug those values into our test statistic, we get a value of 2.12 for our test statistic. So this particular test statistic is actually called a Z statistic, and you might recognise that the calculation has the same form as what you came across when we calculated Z scores for individual values in our sample. In that case, each individual was measured in units of standard deviation away from the mean. In this case, we're measuring the observed point estimate in units of standard error away from the hypothesized mean. And we can use this Z test statistic because we have a large sample and we expect the sampling distribution of the test statistic to be normal, and we'll explain more about that in later videos. So we now get to the exciting part. We compare our test statistic with the sampling distribution of the test statistic under the null hypothesis to calculate our p-value. So as we said in our example, we use the Z distribution, or standard normal distribution. And you've seen this before, it looks like this. So the area underneath this curve between two Z statistics represents the probability of obtaining Z statistic, or a test statistic, within that interval. And for example, we know from the 3 sigma rule that the probability of having a Z statistic between approximately -2 and +2 is equal to 0.95. That captures around 95% of our test statistics under the null hypothesis. So the exact interval for a 95% probability is plus or minus 1.96, so it's kind of a little bit around here. So let's see where our Z statistic that we calculated, our test statistic, where that fits into this distribution. So the value for that was minus 2.12, which is around here. So we want to calculate this area contained here, which would represent the probability of obtaining a test statistic as low as what we observed, if in fact there's no difference in between these babies of deprived areas versus the national average. So we usually use statistical tables or a computer program to calculate that probability, and we get a value of 0.017. There's about a 1.7% chance of observing a mean birth weight as low as what we saw if in fact the mean birth weight in deprived areas of Bristol is the same as the national average. Now this is what is called a one-sided test, or one-tailed p-value. We've basically calculated the probability of obtaining a sample mean as low as what we did given the null hypothesis. However, the test statistic could have been positive, or plus 2.12, so the result could have gone in the other direction. In that case, the mean birth weight in the deprived areas would have been greater than the national average. And typically we tend to calculate what's called a two-sided p-value because we don't specify the direction of the difference. We just say what's the probability of obtaining a result as extreme. In order to calculate a two-tailed p-value, we have to add on the probability of obtaining a test statistic as big as 2.12, and because it's a symmetrical distribution, this area here is the same as this area here, so we just double this value, times it by 2, and we get a p-value equal to 0.034. So I'm going to repeat myself again and again and again as to what a p-value is. So let's say it again. The p-value is the probability of having observed a result or a more extreme result when the null hypothesis is true. So in our case, the null hypothesis was that birth weight is equal to 3.4 kilograms in the babies from the deprived areas of Bristol. So our p-value of 0.034 indicates that it's reasonably unlikely to observe such a difference if the null hypothesis is true. In fact, we'd expect to see a difference of what we saw, which was 0.18 kilograms in less than 3 or 4 occasions out of 100 if we were to repeat the study with independent random samples again and again and again. So based on this p-value, we might therefore decide to reject the null hypothesis in favour of the alternative hypothesis that there is a difference in birth weight between babies born in deprived areas of Bristol and the national average. So we use the word reject here. The alternative, if the p-value is very large, would be not to reject it. Now, we never accept a null hypothesis or say that this is proof of a hypothesis. We'd only say that we failed to reject it. And the reason for this comes down to logic. To prove a hypothesis, we'd have to measure the entire population, and all observations would have to behave consistently with a hypothesis. This is rarely done and is rarely achievable. For example, Karl Popper, the famous philosopher of science, in his work on the philosophy of scientific discovery, used the example hypothesis that all swans are white. So even if we went out and observed many samples of white swans, it does not necessarily mean that we won't find a black swan in the next sample. I.e., just because A is followed by B on hundreds and thousands and thousands and thousands of occasions, it doesn't mean that A will be followed by B on the next occasion. The point is that trying to prove a hypothesis is logically impossible, as we generally don't measure the entire population. And as we saw, some target populations are notional. For example, the true behaviour of something. So they're a bit kind of out there in the universe, otherworldly. So their population can be infinite. However, we can disprove or falsify a hypothesis by looking for observations that are unlikely under that hypothesis. And the p-value is an indication of the strength of evidence against the null. Is it false? It is not an indicator of proof of the null. And Einstein captures this beautifully in a letter to Popper, where he states that no amount of experimentation can ever prove me right. However, a single experiment can prove me wrong. So the p-value reflects whether this difference we observe could be due to chance. But what threshold should we use to reject a hypothesis? The choice is somewhat arbitrary, although many studies use a threshold of 0.05. The result is said to be significant if it's below this threshold and not significant if it's above. And you may hear the word significance testing in place of hypothesis testing. A threshold of 0.05 means that 1 in every 20 times we'll reject the null hypothesis when it's actually true. This is called the false positive rate, or alpha, and we'll discuss that more in another video. So the literature is abundant with p-values, but unfortunately they're misused very often too. And this has been harmful to the scientific and medical literature. Publication bias is strongly apparent. This is where researchers selectively report findings that reach their 0.05 threshold, and editors of journal favour publishing these results. But p equals 0.05 has no special importance, Consider, for instance, two studies on the same topic, same sample size, etc. One finds a p-value of 0.051, another a p-value of 0.049. In one case, you'd reject the null hypothesis, and in the other, you'd not reject it. It's arbitrary. So hopefully our discussion of p-values has allowed you to think of them as a continuous indicator of the strength of evidence against the null hypothesis, which is encapsulated in this diagram. So this is actually the spirit that R.A. Fisher intended when he came up with the idea of hypothesis testing way back in 1925. And there has been a concerted effort over the last 2 or 3 decades to re-educate scientists to interpret them in this way. Unfortunately, it's easy just to say p is less than 0.05, therefore the result is significant. But this is not actually interpreting the p-value, it's just using a rule or an algorithm. Interpreting the p-value as the strength of evidence against the null in the context of the study attached to the p-value requires some understanding of what a p-value is, which is much more difficult. A common misinterpretation of p-values is to link the p-value to the hypothesis rather than to the data. For example, saying that it is the probability that there's no effect, or saying that it's the probability that the null hypothesis is true. In our example, this would be like saying that our p-value is the probability that the birth rate of babies in the deprived areas is the same as the national average. This can be summed up by the following bit of notation that's often used in probability. So this means the probability that the hypothesis is true given the data we've observed. This is wrong. What the p-value actually refers to is the probability of the data given the hypothesis. So expanded a little more, it is the probability of observing such extreme data given the null hypothesis is true. That's about the 5th time I've said that. In the statistics we teach, this is not the information that the p-value provides. And it's important to get this right, not just to ensure that we report results correctly in journals, but also for the way in which you think about statistics and science. The data are the random element to an experiment, as we saw when talking about sampling variation. The hypothesis is fixed, and we find evidence against it. Understanding that a p-value is the probability of data given hypothesis, I think allows you to have a better intuitive feel for a p-value as a continuous measure of the strength of evidence against a null hypothesis. It allows you to interpret p-values in a more informed way. The wrong interpretation of probability of hypothesis given data, I think, encourages us to think about p-values in a dichotomous way, significant or non-significant, reject or fail to reject, etc. There's generally an over-reliance on the reporting of p-values in the literature. Rarely should they be reported on their own. You should also include a measure of effect and a confidence interval. And a p-value is directly linked to a confidence interval, so a bigger study with the same size effect or same point estimate, as illustrated here, would have a much smaller p-value. So you can see here that a p-value is not a measure of the size of the effect or the effect size. We could also have a larger study that has a very small effect but a very small p-value because it's so big, and a smaller study with a much greater p-value but a much larger effect. The size of the p-value reflects the statistical significance of the study, not the clinical significance. So these are two different things. The point estimates and confidence intervals are thus also required to deem whether something's clinically significant as well as being statistically significant. So that was an overview of the structure, the philosophy and logic, and the interpretation of hypothesis tests and p-values. There's still a lot more to cover on this topic. We haven't gone into things like what tests you should use when, etc. And that really comes down to what is the appropriate test statistic for our research context. And We also haven't talked about the validity of these tests. So for now, we just assume that they're all valid, but they can fail to give valid results when certain assumptions for the tests aren't met, and we'll discuss that much more in later videos. So here's a fairly long list of new terms that have been introduced in this video.